Everybody, welcome back. In this video, I want to talk a little bit about biconditionals, introduce the concept. Now, biconditionals are another kind of connector statement. We've talked about conditionals, we've talked about conjunctions, we've talked about negations. These are biconditionals. Biconditionals are basically two sets of arrows. So you're saying that the arrow goes in both directions. So if I have A arrow B, and I say, and I also have B arrow A, and let's say, let me actually go ahead and put it this way. If I say I have these two things together, if I have A arrow B, and I have B arrow A, I'm saying if you've got A, then you've got B, and if you got B, then you got A. In effect, I'm saying that the arrow goes in both directions. So this is actually not a well-formed formula as it is. There's nothing wrong with it per se, but there's a more efficient way to write it. Again, it's kind of similar to like if I said, and I've said something like this before, but if I said, if write 5 on the board, and you go 1 plus 1 plus 1 plus 1 plus 1. Again, that's true, but there's a more efficient way to write it, namely that. So this is, while this is equivalent to this, certainly, there's a more efficient way to write. Instead of saying 1 plus 1 plus 1 plus 1 plus 1, you can just write the numeral 5. So similarly, if you're saying that you've got an arrow going in both directions, A leads to B and B leads to A, or vice versa, the simpler way to write it is simply to write A double arrow B. Now, because the arrow is going in both directions, you could actually write it this way too, and that would be totally fine, because there's no real left or right here because the arrow is going in both directions. Now, what I want to explain, and I already have on the board, is the kinds of language we could use to mean precisely this. So what we've got here, basically combinations, and I know you've heard these phrases before, especially the first one. I think you probably remember from, say, geometry, even if you don't remember what it means. We got this. If I said A, if and only if B, how would I write that? Either one of these. Now, I prefer to, whatever letter comes first, I'm probably going to stick that one on the left, but with biconditionals, it really doesn't matter. You could write it this way, and that would be fine. So if I said A, if and only if B, that would be A double arrow B. Because think about it. I'm saying A if B. Well, that would be this. That would be if B, then A. But I'm also saying A only if B. Remember, we draw the arrow through it. That would also be A arrow B. I'm saying I've got A if and only if B. I'm saying both these things, but the most efficient way to write it would be this way. Now here's other equivalent expressions. They mean the exact same thing as if and only if. Also, there's an abbreviation, especially in mathematics, where people say IFF. If means the same thing. It's just short for if and only if. I could also say A is a sufficient and necessary condition for B. Well, think about it. Sufficient conditions go on the left side of the arrow. Necessary conditions go on the right side of the arrow. If I say something is both sufficient and necessary, I'm saying the arrow goes in both directions. Now, I could also flip these terms around here. I could say A is a necessary and sufficient condition for B. What would that produce? The exact same thing. I could also say A exactly if B. This is a little bit more of a technical expression, but I could say A exactly if B. That means the double arrow. I could say A just in case B. That's a little bit more of a technical thing. Usually when we colloquially say just in case, we typically mean just a regular conditional. So that one's a little bit confusing. But if you ever see any of these italicized on your quizzes, that means to employ the double arrow here. I think actually the exactly is fairly obvious, because I want to give an example of where you would have, so to speak, in real life biconditionals. Because what you're saying is it leads both one to the other. So consider this. If I say something like a triangle, a geometrical shape is a triangle if and only if it has 3 sides. That means if it's a triangle, then it's got 3 sides. And if it's got 3 sides, that's a triangle. So that's a true biconditional statement. Triangularity means 3-sidedness. So that it's exactly the case. Do triangles have 3 sides? Exactly. But then there are some biconditionals that don't work. So if I said something like this, something is a rectangle if and only if it has 4 sides. Well, let's break that down. What would that be? If something is a rectangle, then it has 4 sides. That works. That's true. But if something has 4 sides, then it's a rectangle. Well, that's not true. That, in fact, is false. So I could even say If something is a rectangle or a shape is a rectangle, if and only if it has four sides, not exactly. Okay, that's where that exactly if comes to the case, or comes to be the case. When we're saying not exactly, we're saying you can't stick a biconditional in there. They're not the same thing. Why? Well, all rectangles have four sides. That's true. But if something has four sides, it's a rectangle. A rhombus, for example, does not necessarily have is not a rectangle, nor a diamond, nor things like that. Okay. I could also employ square here instead. You know, something just because something has four sides, does that mean it's a square? No. And again, I've given you a couple of geometrical examples. So that's where these biconditionals would not work. So in the next video, I'm going to do a quick refresher on the rules that we can use with biconditionals. They're pretty straightforward. I've actually kind of already indirectly gone over them.